A cloudy blue haze appearing on a dog's eye marks a critical structural failure of the transparent cornea. Historically, this was the signature of Canine Adenovirus Type 1, the pathogen behind infectious canine hepatitis. This list of clinical signs tracks the acute stage of the infection. The virus aggressively targets the internal organs, manifesting as high fevers, jaundice from liver damage, and severe abdominal pain. When a young dog survives this initial assault, their systemic symptoms recede. The fever drops, the liver stabilizes, and the animal enters a period of apparent recovery. Then, 7 to 10 days after the life-threatening illness vanishes, the dog's eyes suddenly turn opaque and blue. This opacity develops in the wake of the infection, a secondary failure triggered by the body's own recovery process, rather than an active viral attack on the eye. For a cornea to stay clear, the eye must maintain a precise internal environment. Specifically, the corneal tissue must be kept relatively dehydrated, holding steady at exactly 78% water. Inside a healthy cornea, collagen fibrils are arranged in a perfectly uniform grid. This specific spacing allows visible light to pass through the tissue without being blocked or scattered. To maintain this grid, a single layer of endothelial cells acts like a microscopic bailing crew. They use specialized pumps to constantly eject excess fluid, preventing the cornea from becoming waterlogged. If these pumps fail, fluid rushes into the cornea, physically pushing the collagen fibrils apart. This disrupted spacing creates a wavelength-dependent scattering of light, giving the eye a blue appearance. Optical transparency relies on this continuous mechanical pumping system, one that is easily overwhelmed by an immune system in overdrive. Even after the virus is cleared from the liver, the dog's body continues a massive internal cleanup called a type 3 hypersensitivity reaction. During this phase, the dog's antibodies bind to leftover viral fragments, forming heavy molecular clumps called immune complexes. As these complexes circulate through the bloodstream, they get trapped in the narrow, delicate blood vessels of the eye. These trapped clusters trigger an intense local inflammatory response. While the immune system is targeting the viral debris, it inadvertently causes massive damage to the nearby tissue, destroying the cornea's water pumps. With the bailing crew gone, fluid rapidly saturates the cornea, resulting in the characteristic blue clouding. The dog's immune system destroyed its own optical water pumps while attempting to clear out the viral remains. This reaction presented a major hurdle for early veterinary medicine. Early vaccines used a weakened version of the hepatitis virus to successfully prevent liver failure. While these vaccines saved dogs from the fatal disease, the weakened virus still generated enough debris to trigger the same immune crossfire, causing vaccine-induced blue eyes in a significant number of pets. Researchers searched for a way to train the immune system against hepatitis without leaving behind the specific triggers that damaged the eye. They looked to Canine Adenovirus Type 2, a related respiratory virus that shares similar biological markers with the hepatitis virus. The Type 2 virus provides cross-immunity against the deadly liver disease, but it lacks the properties that set off the destructive immune reaction in the cornea. Since this switch, vaccine-related blue eye cases have fallen to less than 1%. Because of this innovation, modern diagnostics prioritize a different list of suspects when a dog presents with a blue eye. Clinicians now look for nuclear sclerosis, genetic conditions like endothelial dystrophy, or the high pressure of glaucoma, which forces fluid into the cornea. The blue eye stands as a historical record of a complex immune mistake, and a reminder of how mapping that mistake allowed science to safely eliminate a fatal disease.